All right, thank you to our early attendees. We are just 2 minutes away from the webinar starting, but thank you for getting here nice and early. We are going to get started in just a couple minutes here, so hang tight and we will be live shortly. Okay, so according to my clock, we are at the top of the hour, so I want to get to the exciting part. So let's get through the intro here. Hello, everybody, and welcome to Quantum Analytics webinar. I'm Lauren Armstrong, Marketing Director for Quantum Analytics, and I will be moderating today's event. Today, we are going to show you how to maximize the power of spectroscopy in your regulated analytical laboratory. And I cannot think of a better person equipped to navigate us through this topic than my friend, Dr. Tom Tagg, Applications Manager for Bruker Optics. Dr. Tagg will be covering the theory of FTIR and Raman spectroscopies and why they work so well for even the most challenging samples. Before I introduce Dr. Tom Tagg, I wanted to share a quick note about quantum analytics. We are a value-added distributor of analytical instrumentation. We are your one-stop shop for the busy lab manager, offering everything from rentals, financing, leasing on new or refurbished instruments. And we also offer consulting services for new lab startups. Basically, anything you need for your lab, we are your company to work with. All right, let me introduce Tom. Dr. Tagg is a member of the Visiting Advisory Committee of the Metropolitan Museum of Art in New York and on the Strategic Advisory Board of Amplified Sciences. He received his PhD from the University of Utah in physical chemistry and a Bachelor of Science in Chemistry from the University of Texas at San Antonio. He is a member of the American Chemical Society for Applied Spectroscopy, American Physical Society, and the Optical Society of America. We are very proud to be partnered with Bruker Optics, which means our US based clients can purchase, rent, or finance the Bruker products you are learning about today directly from Quantum Analytics. All right, as a registered guest, you're going to receive a link to this recorded webinar in your email when it becomes available, which usually takes about a couple hours. We've reserved about an hour for this webinar, including Q&A. So type your questions at any time into the text box in the question module that you see on the right side of the screen. We're going to be keeping a roster of the questions and pose them to Tom at the end of the webinar. Also, we're going to be asking a poll question at the beginning of the webinar. So when that poll question pops up, simply choose the best answer and we're going to review the results with the group. All right, that ends our introduction. So without further delay, I present to you Dr. Tom Tagg. Take it away, Tom.
Great, thank you, Lauren. I'm excited to talk with you today about maximizing the power of spectroscopy in your regulated analytical lab. This is a little different than some talks because we're actually going to talk about infrared and Raman spectroscopy and microspectroscopies and how they can help you within the confines of even the most demanding regulatory regulations. And as we do that, we'll see some beautiful examples from the polymer industry, the pharmaceutical industry, and some of the applications that are most interesting that we see have the greatest impact, such as reverse engineering, or trying to identify those annoying contaminants that don't belong there. So with that, we're actually going to do the poll question right at the beginning here, and the reason is it's very relevant to the topic that we're talking about.
Fantastic. All right, as promised, everybody, I'm going to launch a poll right now. So there it is. How would you rate the regulatory requirements of your lab? So select one of the following. Would you describe it as onerous or difficult, time consuming? Would you describe it as manageable, easily achievable or routine, or not an issue? Pick the best one for you, and we will look at the results in just a second. All right, I'm going to give it one more second. It looks like we are good. All right, I'm going to uh, stop the poll. And here's the results. Wow. So 43% not an issue, 29% easily achievable routine, 14% manageable, 14% onerous or difficult. So it looks like we kind of have a little bit across the board here, Tom.
Well, thank you, Lauren. That's a really interesting issue because even when you visit a physics department these days, usually there are some regulatory issues that have to be addressed, even if it's just making sure that the data is saved in such a way that it can't be accessed outside the organization. So, okay, so moving on from that, why spectroscopy? That's really the question, right? So the first thing to recognize is that every molecule has its own fingerprint signature in the middle infrared region of the electromagnetic spectrum. So what does that mean? It means that every absorption or Raman spectrum from a molecule is actually going to be unique. So it's very highly specific, which is great. So if you want to identify unknowns, there's absolutely no way that you could do better with any other technique. The other issue is whether the technique that you might employ is a destructive or altering technique. So FTIR and Raman are not destructive and non-altering. So they're what we call front of the line analysis techniques. And you can see one of my colleagues there holding the alpha. The bench space sometimes is an issue when building out your lab. So these spectrometers don't necessarily have to take up a lot of room in your lab. So when we talk about vibrational spectroscopy, what type of things can we learn? The first is we can identify unknowns, right? The material identity. Sometimes that's not as useful as you might think, and then you have to go to the functional groups. Is it a carbonyl? Is it an amide or such? And that can give you a hint. You can also look at reaction dynamics and be able to look at the reaction progress or dissolution if you're looking at tablets sometimes, and look at that in time. You can look at homogeneity and distribution, which for a lot of products is becoming more and more important. Crystallinity, polymorphism, and such, what I would call solid state chemistry, those things are very nicely probed with vibrational spectroscopy. And looking at purity, how good can you do? Well, if you're looking to see minority components in the infrared, you can do certainly 1%, 0.1%, even 0.01%, where the limiting factor actually becomes how well you can build a calibration set to train your chemometric model. Some of the places where you can see these techniques employed every day are in R&D, development, science, as well as in quality control, looking at a product that may have a defect, or maybe a food product that has a particle in there that is not supposed to be there. One of the most common is in food products, there might be a bone or something that is not so palatable from the customer's perspective. Why the middle infrared region of the electromagnetic spectrum? So when we look at the mid-IR, this is where we're looking here. And you can say, okay, I go to the near infrared by going higher in energy, or to the visible and to the UV and X-rays. In the other direction, you go to the far infrared, microwaves and radio waves. And in the chemist world, we're doing 4,000 to 400 wave numbers, and in the physicist world, that's 3 to 30 microns. That's where the ground state to the first excited state vibrationally those transitions are. Whether you're accessing them by Raman or IR, that's the region you're going to look. In the near infrared, we're accessing higher order vibrational transitions, and those are less facile or less probable. So you have less sensitivity in the near infrared and less specificity. But because of those things, sometimes you can integrate over more matter. So if you're looking to quantify inhomogeneous things like grains or other things, because you're integrating more matter, the quantification accuracy can be better. When you look in the far-infrared, what information do you get there? That's where you get solid state modes or looking at polymorph differences. And you also can see organometallics. So just prior to this webinar, I have a guest visiting with me today, and she has a really wonderful painting, and we're looking at the media, what is the paint made out of, and we've found so far that we have an alkyd enamel that we use the infrared to do the analysis for, and then what are the pigments? We actually use the Raman for that because most of these pigments have metals in them as the center to the key molecules, and those are more evident in that far infrared region that is accessed by Raman best of all. Okay, so in the infrared, we're going to look at the interaction of the molecular dipole moment. We have to have a dipole moment in order to get the mid-IR result that we're interested in. And in the Raman, we're actually looking at the Stokes, or the energy loss from the incident light. And we also have the anti-Stokes, where we start at the first excited state and decay down to the ground state. And in the Stokes, we're exciting up to the first excited state vibrationally to be able to collect the Raman data. So let's start with IR. What we're going to do in building a simple instrument is we're going to have the IR source. The source hits the sample. We'll collect the reflectance data or the transmission data or ATR to access that information, and then we'll detect the signal. And when we do this, we're looking at the light that is absorbed by the molecules. So we'll send broadband radiation onto the sample. The light that gets absorbed, as indicated by the weaker signal on the left, is due to the absorption of the molecule, and that gets translated to the molecules vibrating at a higher order. For the Raman effect, we're going to send monochromatic light onto the molecule, in this case a simple benzene atom, a benzene molecule. We're going to allow the light to bounce off either elastically, as shown by the green, or inelastically by the red and blue, where we have a shift to higher or lower energy. As it turns out, the most common event is actually where nothing occurs and the laser light passes through unabated. When we look at the Raman, we can see that only 10 to the -4 of the light actually gives you the elastically scattered, the billiard ball effect of the Rayleigh scatter. Or you can also have fluorescence, where you have an attractive potential energy surface where you have a transition that would yield fluorescence. As it turns out, that can be a very bright or efficient process and can dwarf the Raman signal, which you can see as much weaker, 10 to the -8 to 10 to the -11 probability typically. So Raman is typically weaker when you want to do a quantification of dilute samples, but it can give you very rich information similar to the IR. It's very specific, and it's very complementary in that because of selection rules, the IR works really well for molecules that are very, very anti-symmetric or asymmetric. And water is a C2V molecule, so it works really well in the IR, but because it's highly anti-symmetric, it doesn't work well in the Raman. So that can be an advantage. So again, things that are weak in the IR typically are strong in Raman and vice versa. So many of the research labs around the country will have those sitting side by side on the lab benches. And Raman is applicable to almost everything that the IR can sample. And it works really well in water samples, right? Because water doesn't have a signal, or very weak anyway in the Raman. And then it works well in the far infrared. And since you're doing the excitation in the visible, you can actually work through glass bottles and vials, plastic packaging and such. The intrinsic bandwidth for Raman is a little sharper than IR, so that can mean that your PLS-based quant or partial least squares quant can be a little simpler, where you can just sit on an integration one band rather than having to do a PLS-based multivariate quant. So in short, you get the benefit of the mid-IR and the far infrared with the sampling benefits of the near infrared, where you can look through vials, you can have very long reaction probes and such. Very cool. But Raman's not perfect, right? One of the things it doesn't do well at is looking at molecules that have low symmetry. and it's not as sensitive as mid-IR. I mentioned it's a weak technique. Fluorescence interference can be common, so you may need to use 2 or more lasers. In general, things that have an aromatic ring fluoresce in the blue-green, but work well in the red. So usually for those, you'll use 785 nanometer excitation, and for 3D transition metal containing species, they typically fluoresce at 785, but work well at 532. Carbon species also work really well at 532, and in the red, they tend to start to heat due to the higher order vibrational modes that are accessible there. For Raman, you also need to at least be cognizant that you're using a fairly powerful laser to do the spectroscopy. For the Raman microscopy, it's a completely enclosed, interlocked, safe system, so it's class 1. And with the Bravo, it's a handheld Raman device we'll talk about, and it actually is designed from the ground up so that it's also a class 1 laser safe product. It's the only one out there in the market that is, and that means that you don't have to have a laser safety program or a laser safety officer or anything like that. The next question I get when we discuss IR and Raman often is we say, okay, how about these databases? I want to collect data from many different things that I might see and then do the IR and Raman. Well, this is a really good example with this simple copper complex. If you collect the IR spectrum and the Raman spectrum, you'll see that the bands are in the same position. It's just that the modes that are more antisymmetric are stronger in the IR and weaker in Raman, and vice versa. But the intrinsic band position is unchanged. Very cool. That means you can really take a library in the IR and search over with a Raman spectrum or vice versa. So just because you might be collecting data in one way, all the data you have historically can still be informational in trying to identify those important unknowns. Okay, we mentioned regulatory issues, so here they are. So all of our systems that we sell into this marketplace are all 21 CFR Part 11 compliant. The infrared microscope, the alpha small FTIR, the handheld Raman. We'll get into that in a second. And they're all US and European pharmacopoeia compliant. So these systems are all permanently calibrated at all times. And Bruker holds a few patents and being able to do this all the time. So it's really important for Raman, where the systems are intrinsically not as stable, and so to have a calibration source built into the spectrograph actually is really important for knowing that the data you get is always calibrated. It also makes the systems much easier to use, and so I'll show that example here most of all. So to do the Raman, you can see we have the calibration standards for NIST traceable on the stage for acetaminophen, silicon, polystyrene, calcium carbonate. Every day, when you set the systems up, they'll actually generate the test report and save it either digitally or in a hard copy for you. And what we normally recommend is to actually do the performance qualification daily. Some people do them weekly, and the operational qualification would be done on a quarterly or semi-annually basis. So again, all of the products, the Alpha 2 small mid-infrared spectrometer, the Invinio, which is the next step up, the Bravo handheld, the Centera Raman microscope, and our IR microscopes, the Lumos 2 and Hyperion 2, all of them have everything configured to work all the time. And again, the performance qualification test, or the PQ, ensures the daily performance, and the OQ verifies that the overall performance over time is good for the instrument. So say you have a source in the IR or Raman that is going to go bad, the system can pick up the changes right in the beginning and allow you to order parts to fix it yourself, or to schedule service so that your downtime is minimized. This is really nice in that in the software in the lower right-hand corner, you'll see a red light, yellow light, or green light. If you get the yellow light, usually it's telling you something is maybe going to go wrong shortly, and you can plan for that. So very nice. So for the microscopy, we want to talk about why look at small areas. So the biggest issues is looking at compliance testing. That's maybe the #1 application is identifying those unknowns. So something that's there that doesn't belong there, looking at reverse engineering at product development and packaging. This is important because if you look and say, okay, I want to develop this, but how do I go about it? oh, well, wait a second, a competitor actually has this functionality in their product. You can buy it and their competitor's product and reverse engineer it and save yourself years off the development time and a lot of money typically. So the next part about getting the answers right is actually having the tools to get the right answer right. So you can use integration of different bands to do quantifications. You can do multivariate quantifications that allow you to account for things like changes in refractive index and scattering properties and such that may be taking place in your samples, as well as concentration. All those can be factored in with a mature quant method. Validating things, so okay, I want to do raw materials ID, I want to compare those with known compounds. Usually the quick compare works exceedingly well, where you take all the things you might ever see, you dump them into a directory, you run those and get the answer, red light, green light operation. Very nice. And then for the chemometric analysis, you can do 3D analysis using multivariate analysis, using evolving factors. You can do neural networking, and newly introduced in the software, actually in the last month or two, is new machine learning AI-based cluster analysis. Really fabulous for getting the right answers and really, really fast. So in the past, if you wanted to analyze a microplastics filter where you have about 15 million spectra, it would take hours to actually, a couple hours to do the analysis. Now they can be done really in about a minute. So the using smart mathematics is really key to doing a good job there. Now, how small can you go? So let's start with the Raman microscopy. So we're going to look at around 400 nanometers limited. If you use a higher NA objective, you can get down to about 1/4 of a micron. And the depth of resolution, you can see the Rayleigh criterion equations here. You can see that the lateral resolution is about a micron for most operations. You get down better than that if you try hard. And the depth resolution with Raman is really nice. You can get down to submicron also. So let's start with an ATR measurement in the mid-infrared. So non-destructive, you just place your sample on the ATR crystal and you do the analysis, and the measurement is done in seconds. This is the best place to start. If you're going to equip a lab, this is the first instrument you want to get, because it's reliable. We have a brazed-in diamond ATR crystal. Sometimes when I do time-evolved studies on epoxies, I actually use a screwdriver and a mallet to knock the hardened glue off the crystal. It's that robust. So here's a good example looking at some rubber O-rings. So here I have 7 of them, and they're high refractive index, no problem. I've collected the data very quickly and easily. You can see Viton black and blue samples, everything that you would want to look at there. And I promised you red light, green light operation. So you do the ident method, and oh, I've got the Buna and sample there, and that's doing the identification of the unknown O-ring. The other thing I think is kind of cool, which again I mentioned, is that you can cure samples right on the crystal. So I like this example. So I've got the before curing here shown in the blue, and then the after curing showed in the red, and you can see very nicely the differences that are picked up using the spectroscopy. Okay, so we've gone with our portable IR. Let's go to the Raman. So now we've got a handheld Raman. The analysis spot size is about the same size, 1 millimeter or 2. It's a class 1 laser safe. The spectral resolution is about 8 wave numbers. In the IR, we typically run at about 4. So you're sacrificing a little, but remember that the intrinsic bandwidth is about 6 to 8 wave numbers anyway, so you're not losing anything really there. We talked about fluorescence being an issue, and in the Bravo, we actually have some patented methods to get around that. So again, class 1 laser safe, we have what we call the SSE, where we shift the laser excitation wavelengths actively to actually strip off the fluorescence, and that's patented by Bruker. We use 2 lasers all the time on the system, so if the fluorescence is bad at one wavelength, it might not be at the other, as I indicated earlier. And again, all that is built onto this little system. Has the built-in wavelength calibration with the neon lamp built right in there, and it complies fully with 21 CFR Part 11 compliance. You can see that you can just scan a barcode and go do the raw material ID. In my investigations today, I actually just put the Raman system, the handheld, right next to the painting and can collect the data without touching it or making any changes to it. Sometimes your sample type might change. So I have the smart tip used for bags and painting objects above, but you can also put a vial tip on there and the parameters are all correctly loaded and everything automatically. This is the SSE in action. So you can see now I'm going to shift the lasers of the two excitation lines around so that I can move the Raman bands, but actually the fluorescence is very broad, so it doesn't change. So you can divide that off and be left with the desired Raman signature. So this is a really good example looking at silicon dioxide, and you can see, wow, there are the two lasers at 785 and 852 shown in the top, and then there's the 1064, even longer wavelength spectrum. But with the Bravo and being able to take the best of both spectra, I can get a really nice Raman spectrum quickly and easily with the system. I was actually visiting a customer and they had a bag of rocks and they said none of these work by Raman, and kind of went back to their office and they said, well, if it works, then come and get me. And about 15 minutes later, I went and got them. I said, well, all your rocks work fine. And he said, no, they can't be. Those things all fluoresce. I said, they may fluoresce on a traditional system, but on the Bravo, they'll work. And so he said, well, these I know don't work. And he went over to his Raman lab bench system and he ran them and he said, see, they fluoresce. And then we measured them on the Bravo and we were able to get good data. It's that big a difference. The second step in being able to do that is actually what we call the concave baseline correction, which is also patented, where we use a series of curves to model the fluorescence and strip it off. So here's a good case of talc. There's the raw spectrum in red. There's the fluorescence removed spectrum shown in the blue. And this is a really fun example where I have a coded tablet shown above, and then the fluorescence removed spectrum in the middle, and then the reference spectrum shown below. And again, you can see that even though you can hardly see any bands there, the fluorescence removal tools work just really nicely. This is one of my favorite examples where we're actually looking at in a lab here at the Morgan Museum, and good friends of mine, Elena and Federica, are using the Bravo to analyze illuminated manuscripts from the 10th century. And you can see that we're actually going to get close to these beautiful illuminated manuscripts, but we're not going to touch them. And we're going to get rid of the fluorescence as described. And now here we can see the indigo, the purple, which is notoriously fluorescing. The paper fluoresces, the indigo fluoresces, yet you can get a good spectrum by stripping off the fluorescence there. In the middle, you can see the red area of the manuscript where lead oxide and lead white and red lead can be identified. And on the right, of course, that orange is vermilion, which many of you are probably very familiar with. It has one of the strongest Raman signatures there of any molecule. So we've looked at the handheld and portable IR and Raman. How about microscopy? Let's look at small samples. So we have, in 2020, we introduced the Lumos 2, and it won the Pittcon Award for the best innovative new product for larger companies. And so in this case, one of the reasons we won is that everything is software controlled, yet it has unmatched quality of data for ATR, reflection transmission, and imaging in all three modes. It's also extremely robust, where it's expected that it will last really about 10 years without needing anything or much longer. So again, the software is something that when we designed the system, we felt was very important. So we use a wizard-based acquisition software that is the same for the Raman and IR microscopes. You can see that the working distance is shown by our model analyzing an art object, and that's exactly what I did today. Was I placed this fairly large painting right on the stage there, and was able to analyze most of the pigments. So you have the largest throat and depth for being able to analyze samples. And again, I mentioned the video wizard. So again, everything is 21 CFR Part 11 compliant. And one of the things you'll notice as far as this software is just amazing. If you look in this case, say I have a bunch of particles I want to analyze, and I don't want to have to mark them one at a time. If you look in the lower left, it says find particles. It'll go and find them on its own and then do the analysis and give you the workup. It tells you what it is, how many of them there are, and they're categorized by size. Really cool. And again, everything is motorized. The ATR crystal, the apertures, the condenser, polarizers, analyzers, everything. Even the switching where we use the higher NA for the IR and the lower NA for viewing. This is the ATR crystal, and you'll see that the crystal comes down. And we actually control not only the pressure, but also the deceleration rates. So for fragile samples, it works really well. The pressure sensor is built into the objective, unlike any other system on the market, just head and shoulders above any other design in the business. So, okay, now I want to do imaging. I've done a few points. Now I want to do many points. And so I'm going to do them just like my iPhone. I can just do the snapshot of the image all at once. So now we can do that. And some of the things that I think are really cool about this is that now you're seeing a live image collected here on the left, where we're collecting about 1,000 spectra per second. And with Raman, it's about 200 spectra per second. And the good news is that these images are processed as you're acquiring them. So even if you're collecting very large data sets, you can actually start the data processing right up front. In this case, just as I'm describing this slide, it's 52,000 spectra, all done quickly and easily. So this is, I mentioned looking at particles, so that one way to do those is to automatically identify them, and then you get the sizing and the identification and the count. But you can also just brute force it. So say you have many particles on there, you can actually collect the full image over everything, and it will generate an analogous result using the AI-based software that I alluded to before. So in the above case, that's 15 million spectra, with 5-micron precision over the whole 1-inch sample. So the nice thing about the targeting approach is that you can choose the size, the spatial resolution, and the minimum object size that you want to characterize or are interested in. And it works for IR and for Raman, and it works exactly the same way. And again, the tabulated results are very easy to understand and to dump into other programs for reporting out. And the microplastics, again, 15 million spectra. It takes about, in this case, for this type of sample, about 15 minutes. It can be as fast as 1 minute, depending on the total time for some of the parameters you're using for the acquisition. And again, you get the count, the size, and the identification. For the Raman now, it's the same type of thing. We're going to use one shot to cover the full range, which is important, and you do the fast imaging. This is a fun example where we're looking at tablets. So we're actually going to go now, instead of filling the full field like we did for the IR, where we're going to illuminate the whole area. In Raman, if you filled the full area rather than going point by point, you actually would be defeating the Raman effect, because the laser power is so important for getting a Raman signal. If you diffuse that power by an area function, you lose power by squared. So in Raman, unlike the IR, we don't want to fill the full field, and we'll do them point by point fast. Now, one of the limitations to doing this in Raman is actually not how fast you can move the stage or how fast you can read the data out. It's how good a data you can get. So in this case, if you can't get good data in half a second, there's no point in scanning more than 2 spectra per second. If you can do it in 10 milliseconds, then you can collect 100 spectra per second. Signal to noise is king in this experiment. And the Centera, because of the way it's designed with a very compact beam path, it has the highest signal to noise. So here's a good example where we're doing a fast map of a tablet, and you can see the area and the concentration where we have high and low concentrations. And then here, when we look at the cross section, we can look at the salicylic acid distribution. This is looking at a nasal spray of the Raman image. And again, you can see this is brand 1 and this is brand 2. And then when we compare the two, you can see that there are some differences in the two polymorphs that the vendors are using. Here's looking at a pain tablet. So you have the acetylsalicylic acid shown in the green below, and you can see the red, green, blue, or known as RGB distribution. And you can see very nicely that this is 1/3 of a million spectra collected, and it's 60 milliseconds per spectrum to get good enough signal to noise to process. And then here we have a different tablet, and this one takes a little longer. This was 300 milliseconds to get a good spectrum. You can see that the spectra are a little noisier with this product. Not a problem. You just take a little longer. And again, you can remove the fluorescence as I talked about. So the next step, which is really cool, and that fluorescence can be removed over the whole image at once. So that was my point there. For a flex focus, what is this? This is the ability to actually do a depth analysis. So you've got your X and Y imaging we've talked about so far. Now we want to look in depth. And so we're going to use an array of pinholes and slits at the entrance to the spectrograph. So we read out the detector in wavelength in the X direction and depth of field in the Y direction. And when we look at the slit as shown below and the pinhole, you'll see that when we use a slit, we eliminate over a range of depths, and so you get information from more than one layer. But with the pinhole, we're looking at a very small area in depth. So that enables us to, in this case, to look at, say, a coating and of a product and where there's coating and not coating just by moving through the focal point. Here's a cross section of a 3-layer multi-layered polymer. Here's a fun one where you can see I have many layers. So rather than doing the area sample where I had to microtome it in the previous slide, now I'm just going to lay the polymer flat. And as I zoom in, you can see that even though we're just 12 microns, I can see each of the different layers very, very nicely. And then here's another issue with Raman over IRs, that due to the confocality, I can look through the bag in a chain of custody issue. Say there's or product, you have a blister pack or any polymer in between your sample and the spectrometer. Raman, you can actually focus on the sample and reject the bag completely. So this is a wonderful example where the drug was found in a suspect's toilet, and then they put it into a second polyethylene bag chain of custody, and you can look through both to get a perfect spectrum. And so with infrared and Raman spectroscopy, I've covered a lot of different things, but IR and Raman spectroscopies are easy to use and highly specific. They're non-destructive, non-invasive, they're fully compliant, compact systems are available at safe space with no compromise in performance. I get that question quite often. People will say, well, should I get an alpha or get an Invinio, the bigger spectrometer? I say, well, it depends on whether you need greater flexibility to go the near infrared or the visible, or you want to do step scan work down to nanosecond resolution, or you want to do some other specialized experiment. The answer is the alpha will perform as well as any other system on the market, actually better than any other system on the market. So unless you need some other feature, you want to go with the alpha or with the Bravo. And then for the microscopy, remember there's a unified wizard-based platform that works really well. And you have state-of-the-art IR and Raman imaging. So Bruker is the leader in this market. I didn't show because of it's a different audience. We just won the PitCon 2023 award for the best innovative new product, and it's another infrared microscope called the Hyperion 2, and it's based on quantum cascade lasers as a laser-based imaging microscope. And again, that's the second gold award for us in 4 years in the infrared microscope world, where we really dominate that market. And in fact, in between those two awards was actually COVID. So that'll tell you how important our position is in the marketplace there. And with that, I'll turn the presentation back over to Lauren, and thank you very much for your attention.
Fantastic. Thank you so much, Tom. We definitely have a few questions here, but I just want to remind our audience that if you have any questions on any of the topics that Tom went through, any questions related to spectroscopy, like this is your guy. So definitely recommend you type them in here. But let's get started. All right, the first question here, Tom, is how easy is it to modify the software to be in line with our lab's SOP?
So what normally happens is when you get the system installed, or if a salesperson sells you the Alpha or Bravo, they'll come in and just introduce it to your lab. They'll ask you a few questions. Do you have an SOP in your lab? And they'll set it up in what we call the OVP, or the operational validation program, which is right there in the software, and they'll configure it exactly as you want or use in your lab. So, okay, I want to do the OQ every 3 months. I want to do the PQ daily, and that's what they'll set up. And the software will be set up to just go from there. Do you want your reports printed out or just saved to disk? So those are just done right up front. You can go back and change those easily yourself at a later date. The user interface is also tiered, which is important. So you can have an administrator or lab manager that can actually have the ability to change different things in the software, and then your operators will not have the ability to do that. And that's the most common implementation that people use.
Awesome. Next question here is, how long does it take to image a tablet?
So that's a great question. So a tablet image with 5 micron per pixel over 13 millimeters in the diameter of a tablet, it takes about 9 minutes only to collect all those spectra, millions of spectra. And in that case, it takes, as I mentioned before, less than a minute to do the quantitative distribution analysis. So the whole thing, start to finish, is under 10 minutes with 5 microns precision.
Awesome. And then next question here is, are any of the systems that you've talked about sensitive to vibrations?
So as it turns out, the smaller ones are not sensitive at all to the vibration. But the microscopes, it's actually the visible microscopy that's more sensitive than the infrared or Raman part. So if you look through the binoculars of a microscope, you can see the sample jitter as someone walks by if you're in a really noisy environment, but the spectroscopy won't matter. What I typically tell people is, in general, when you go into a lab, and if you just put your hands quietly onto the table, if you feel a lot of vibration, then you might want to have some vibration dampening mechanism, maybe some mouse feet, or put mouse pad underneath it, or something else. But by and large, these are very, very robust instruments with respect to vibration. In fact, I take them and put them in my vehicle, and then in my backpack, I take them out to caves to make measurements, and even the microscopes I've done this with to do things pretty much out in the field. So they are very, very durable and very free from vibration interference.
All right, next question is, we are located in a high humidity environment. Does that cause any problems?
Usually, and historically, that would be a problem, because if the components were made up of a KBR beam splitter or some other material that picks up water, that could be a problem. But now it doesn't matter, because the systems are smart and they will pick up moisture. The Raman systems, it doesn't matter ever, but the IR systems, if you choose to have KBR optics, the software will tell you anyway. It'll tell you by that little button in the lower right-hand corner, it'll go yellow and tell you it's time to change your deskant. So the system is smart. It takes care of itself.
Fantastic. And the next question I have here is, are library searches always effective?
Yeah, that's the $24,000 question people always want to know. And the answer is, the library is as good as what the information you put in there. So if you are doing true unknowns, it's really tough to actually purchase a library that's going to cover a full breadth of everything that's ever been made. So what I normally recommend is for you to build a library of your own of the things you see most often, the most common contaminants. Like, I went down to one customer, and it was actually down in Florida, and they were like, well, I'm not getting the #1 compound for my match. What is it? And I looked, and under the microscope, and I saw that it was kind of purple color. I looked up and saw these gloves there, the nitrile gloves, and it turned out, I said, well, I don't need to collect the data. It's probably that. And it turned out to be that. Somehow a glove had gotten into their vat for tablets, and there was some of the glove in the press tablet that they were looking to figure out. So the answer is, they're not always perfect, and when you when you can do your own libraries, it's optimal. Sometimes you'll be on the second hit will be best, or the third, or the fifth, or the 10th. So you actually need to look at them. And during our training for our customers, we talk about spectral interpretation at great length to try to help you to develop your own methodology for getting the right answer.
Fantastic. Um, I think that brings us to the end here. That is, yeah, I just want to make a comment to everyone that if you're interested in getting some more information on these products, we've done a few of these webinars with Dr. Tom Tag, and they are all on our website at lqa.com. So I encourage you to visit our resource library. And if you're interested in specifically polymers, or if you're interested in forensic analysis or wanting to take a deeper dive into the ATR technique or reverse engineering and quality control, going into more of the Lumos instrument that Tom mentioned, we have a ton of great resources available to you to dive into more other specific topics. But before I let everyone go, Tom, thank you so much for your time today. This has been an awesome session. You've done it again. I can always count on you to give a great presentation to our audience here. Everyone, again, if you registered for today's event, you're going to get the link to this recording once it's available. And everyone, have a great rest of your Wednesday, and we look forward to helping you in the future with your analyses. Thank you, everybody.
Thank you, Lauren. Thank you, everyone.
Bye now.